Okay, 6.4, we're looking at accumulation functions. So if you recall from last section, this notation, the integral from a to b of f of x dx is the area under the curve f of x from a to b. Okay, we're going to call capital F of x equal to the integral from a to x of f of t dt. We're going to say that's the area under f of x that starts from a and extends to some x. Okay, now a is going to be a constant. So this is a constant. But we don't know what the x is, so the x is kind of sliding. Like it might go from 0 to 2, it might go from 0 to 4, it might go to 0 to 5. Because x is our variable that we're actually evaluating, we're putting f of t dt here as like what they call a dummy variable, just because it's confusing to have the x and the x there and also in the equation, although it would be okay to do that. Okay, this is called, you can call it an accumulation function or an accumulator function, depending on what you're looking at. But it's adding up the area as it goes along. Okay, so let's look at this function over here. This is going to be the graph of f of t, little f of t. Okay, I'm going to use the graph of f. This is little f. In the figure, to find the values of the table on the interval from 0 to 5, and I'm evaluating capital F, which means I want capital F is the integral from 0 to x of f of t dt. I want the area under the curve of f of t, which is this, starting from 0 until whatever they tell me the value of x is. Okay, so I'm starting from 0. So if I start from 0 and I go to x equals 0, I'm finding the area from here to here, which means it has a width of 0. So the area is just going to be 0 here. Okay, now I want the area under the curve from 0 to 1. So from 0 to 1. Now I'm finding the area from here to here. So I'm finding this little piece right here. Okay, well, let me see. That's going to be 1 unit plus 1 unit plus that's half a square. So that's going to be 2.5. Okay, now I'm going to evaluate the area under the curve from 0 to 2. So let's go from 0 to 2. From here to here, the area under this whole curve. So now I'm extending all the way to here. And then I'm going to add up the area of this thing. Okay, let's count it. That's 1, 2, 3. And I have these two little halves. So now I have 4 square units under the curve. Okay, now I'm going to go from 0 to 3. So now I'm going all the way out to here. So what was this? This was 4, and now I'm adding on 1 more square, so now I'm up to 5. Okay, now let's go from 0 to 4. No, yeah, 0 to 4. So I knew that from here to here was 5, so now I'm going to add on this little half square, so 5.5 now. Okay, now I'm going to go all the way from 0 to 5. Okay, 0 to 5. Okay, let's think about this one though. 0 to 5 is all the way to here. So let's see, 0 to 3 was 5. And then I added on this half square. Since this is below the x-axis, I'm going to subtract this half square. So this was 5. Add the half square, subtract the half square. I'm still at 5. Okay, so that's how the accumulation function works as you're looking at it. Okay, we're going to look at the fundamental theorem of calculus, and this is actually part 2. We have not done part 1 yet. We will do it soon. Okay, so fundamental theorem of calculus part 2 is saying if a is a constant, so this is some constant value, and f is a continuous function, then the derivative of the integral of f of t dt is going to equal to f of x. Okay, why is that? Okay, I'm doing the derivative of the integral, and then somehow it cancels out, and I just end up with this x up here. The a doesn't really matter because when I do the derivative of a, it ends up being a constant. It ends up being 0, so it goes away. The moral of the story is derivative and integrals cancel each other out, or they're inverses of each other. Okay, derivative, integrals, inverses of each other. They cancel each other out. They're the opposite functions of each other. They're inverses. Okay, we normally use the lowercase f of x to represent the derivative of the capital F of x. And that means that the opposite is also true. Capital F of x, which is normally the integral, is also called the antiderivative of f of x, and that's because it's like the inverse derivative of f of x. They are inverse functions of each other. Okay, now let's consider an application of the fundamental theorem of calculus. So in this case, they're saying capital F of t is the integral from h of x to g of x of f of t dt. Then f prime of t, so I want to take the derivative of this function right here. I know derivative and integrals are inverses of each other, so they should cancel out. But I'm not plugging in a and an x here. I'm plugging in these weird functions. So when I take the derivative, I need to respect the fact that I'm actually plugging in a function. So the derivative of the integral should kind of cancel this out. But the upper limit is g of x. So if I did f of g of x and I was taking the derivative, the f of g of x is fine. But chain rule says I have to also take the derivative of the g of x. Since there's a lower limit that's not constant, I'm going to plug in the minus f of h of x, and I'm going to times it by h prime of x. Okay, so they do cancel out, but we have to respect the fact that we're plugging in functions, and we need to take the derivative of those functions. Okay, now there is a special case of this application, and it's this one here. So what if the function, there is an upper limit that's a function, but the lower limit is still a constant? Okay, now if I take the derivative and the integral do cancel each other out. So I would get f of g of x, and then to respect the derivative of g of x, I would do g prime of x. Now according to this, I should subtract the derivative, or I should subtract f of a, but then I'm going to times it by the derivative of a, and since the derivative of a is 0, it goes away. So if this is a constant, I only consider the upper limit. Okay, let's try it to see what this is going to look like. Okay, so I'm going to find capital F prime of x. They give me f of x. Okay, so I want f prime of x, which means I'm taking the derivative of the integral, which means they should kind of cancel out, but then because this has an x in it, it doesn't exactly cancel out. Okay, so they're going to kind of cancel out. I'm going to get sine of, and I'm going to plug in the upper limit, x to the third. But because I can take the derivative of x to the third, because it's a function, I have to times it by 3x squared. Okay, now since the lower limit is a constant, I don't need to worry about it because once I take the derivative of the constant, it's going to go to 0. So this is what f prime of x is. I am going to clean it up a little bit because it looks weird like that. Okay, so I'm going to move the 3x squared to the front times the sine of x to the third, and we normally do that just so that we don't get confused about the argument of sine. The sine is of x to the third. This happens to be multiplied at the end. Okay, and then that's my answer. Okay, let's look at the next one. Okay, they give me capital F of x. I want f prime of x. F prime is the derivative, but I do know derivative and integrals are inverses of each other, so they kind of cancel each out as long as I'm respectful of the derivative of each of the arguments. Okay, so I'm going to let me plug in the upper limit. So 5x. The derivative of x is just 1, so I could times by 1, but really it's just going to go away. Okay, now since the lower limit is a variable, I'm going to do the lower limit as well. So I'm going to subtract, and I'm going to plug in negative x. And then to take the derivative respectfully, I'm going to multiply it by the derivative of negative x, which is negative 1. So this is going to be 5x minus negative cancel. So I'm going to have 5x minus 5x, which is actually going to go down to 0, isn't it? So f prime of x is equal to 0. Okay, let's try 2 more. Okay, so this is capital F of x. I want f prime of x. Okay, I'm going to take the derivative of the integral Derivative and integrals are inverse functions. So I know they're going to kind of cancel out. So let me do h, and I'm going to start with the upper bound of 4x. And then because I plugged in 4x, the derivative of 4x is 4. Okay, now I need to plug in a constant here, but I'm going to skip that because once I do the derivative of the constant, that part's going to go to 0. Okay, I don't know what the h function is, so I'm going to leave it like this somewhat, but I'm going to just make it look a little nicer. I'm going to move the 4 to the front. So this is 4 times h to the h of 4x, whatever h of 4x is. Okay, one more. Okay, derivative of capital F. Okay, this is capital F. Capital F is an integral. The derivative of the integral and the derivative are inverse functions. They cancel each other out. So let me just plug in the upper limit. So that's going to be 3x squared minus 3x. But then the derivative of 3x is 3. So let me times this by 3. Okay, and then I'm going to subtract because there's a variable in the denominator. Let me plug in 2x. So I have 2x squared minus 2x, and then the derivative of 2x is 2. Let's simplify this. 3x squared is 9x squared times 3, 27x squared minus 9x minus 4x squared times this 2 minus 8x squared. Okay, minus 2x times 2 is minus 4x, and then times this minus positive 4x. So this is going to be 19x to the second minus 5x.